Let's solve another problem on circular motion. The problem here says a cyclist is riding with a speed of 27 kilometers per hour. As he approaches a circular turn on the road of radius 80 meters, he applies brakes and reduces his speed at the constant rate of 0.5 meters per second every second. So over here, this number gives me an idea about the acceleration. 0.5 meters per second essentially means 0.5 meters per second square. What is the magnitude and direction of net acceleration of the cyclist on the circular turn? So clearly in this question, when the cyclist is negotiating the circular turn, or in other words, when he is within the circular motion, his speed is also changing. So this problem is an example of non-uniform circular motion. So we have to use those concepts, and ultimately we are supposed to find the magnitude and direction of net acceleration acting on the cyclist. So first of all, we'll visualize the motion of the cyclist along the circular turn. Let's say this is the circular turn and the cyclist was negotiating the turn like this. This green spot is the position of the cyclist at this instant of time. Now clearly if his velocity is u in this direction and he has applied brakes, means there should be a tangential acceleration slowing its instantaneous velocity down, and it should act in the opposite direction of its instantaneous velocity. So this direction clearly becomes the direction of tangential acceleration at. Now also to negotiate the circular turn, he needs a centripetal acceleration to stay in the circle. So that centripetal acceleration will act towards the center as AC. The radius of circle given to us is 80 meters. Now if I convert all the kilometers per hour values in meters per second, it will be velocity of 27 kilometers per hour will simply be 7.5 meters per second by the conversion factor of 5 by 18. And similarly, magnitude of tangential acceleration will become 0.5 meters per second square, as I showed you in the problem itself. 0.5 meters per second becomes 0.5 meters per second square. Now in this problem, you can clearly see if I calculate the net acceleration, it will be a vector sum of tangential and centripetal accelerations, because these are the only two accelerations acting on the cyclist, and by parallelogram law of vector addition, this line essentially gives me the net acceleration. Now this angle is theta, we have labeled it as theta. Now we proceed on to calculate this value. Clearly the AC value or the centripetal acceleration is given as v square by r, and in our cyclist's problem the value of v, or in this case u, is given as 7.5 square by 80. This comes out to be 0.703 meters per second square. From the given things in the question, we have calculated the value of centripetal acceleration. Now for net acceleration, it is simply square root of AC square plus AT square. From this diagram of parallelogram, you can directly see. And from here we obtain the value of AC as 0.703 whole square and AT as 0.5 given in the question. The result comes out to be 0.86 meters per second square. Now clearly this is our net final answer, because these are the only two possible accelerations acting in the question. Now the problem has also asked us to identify the direction of net acceleration. Now from this figure, I know the direction of centripetal acceleration and tangential acceleration for sure. So if I identify the value of angle theta, I can find the direction of net acceleration also. So now in this triangle, you can clearly see cos of theta can be written as AC upon A net, and I know the magnitudes of both AC and A net. So if I apply the same formula, I can write it as cos theta is equal to AC upon A net, which indicates theta is simply cos inverse of AC upon A net. Now AC value is 0.703, we actually found out here, and the A net value is 0.86 from here. This ratio, upon solving and applying cos inverse function on it, gives me 35.43 degrees as the angle. So the direction of net acceleration is 35.43 degrees away from the centripetal acceleration AC. So here we have found both the direction and magnitude of our net acceleration acting on the cyclist. Remember, if the cyclist would not have applied the brakes, there would have been only one acceleration acting, which was centripetal acceleration, and that would have been the net acceleration. But only because the cyclist applied a brake, there was introduction of tangential acceleration, and now the vector sum of both AT and AC had to be taken into account for the net acceleration. I hope these ideas are very, very clear to you. Thank you.